Good morning.
Hello.
We will continue our work. We will continue our work with our section 9.6, solving more problems today. I really encourage everyone be very active because it will be very helpful for you. And if you have at the beginning any questions, please don't hesitate to ask me to help you to be released from any confusion. Can you see and hear me well?
Yes.
Yes.
Don't be surprised by new surrounding. I am just trying to find more comfortable place in my house. Okay. Do you have questions which you'd like to address to me?
No, not
Okay. So let me show what we did the last time. This is that problem on page 392. The boxed is the answer for that particular problem. But below that, I just showed you how the same answer would look in trigonometric form. You can find many similarities. Practically, I used Euler's formula to convert polar form into trigonometric form, as you understand. Yeah, we definitely can convert one form into another form because, as we already talked about that, any complex number can come in three different forms: algebraic form, trigonometric form, and polar or exponential form. So, but we talked also about what kind of operations preferably should be performed in the certain form. And I'm again repeating what I just said yesterday. If I need to add or I need to subtract complex numbers, definitely the best form would be algebraic form. But starting even with simple, let's say, operation like, for example, multiplication, another simple operation, division, algebraic form will be not the best form to be used. This why I will definitely show you how to perform these operations in polar form and trigonometric form. But before we do that, I would like to solve another problem from your textbook. It is on page 392. We solved problem number 6, which I just showed you on that paper, and where we expressed the complex number in the polar form when originally it was given in its algebraic form. If you have any other question about any problem from 1 through 6, please tell me about that. If you don't have any problems with these problems from that spot, I prefer to solve some problems right now from 7 to 14, where we need to perform operation. At the same time, we need to give our final answer in the algebraic form of the complex number. Okay, this is why my question is, should I choose right now one problem from 7 to 14 to start working with that problem, or I need to go back to the previous spot and solve one of problems from that spot? So the new set of problems or from the old? Just give me your reply so I will know what to do.
Can we do 7 to 14?
Do you mean 14?
Yes.
Yeah, I definitely will do number 14, but before that, I like to show a different problem. I definitely will show you this because again, it is probably for you a little bit more challenging than the others. But can you please first choose one problem from 7, let's say, to 12?
7.
7. Okay, number 7. Let me copy that problem. This is again from page 392. Problem number 7 is 2 plus 3i squared. This is that problem, 2 plus 3i squared. Our goal is to find the square of that number and provide final answer in algebraic form. From the beginning, what do you see here? Is it given in algebraic form?
Yeah.
Guys, can
Yes.
you please be more active because I constantly just hear 1, 2, maximum 3 voices. Why all other students are so silent? Can you please participate? Is it in algebraic form?
Yes.
Yes.
Yes. Is it square of that binomial?
Yeah.
Yes.
Is it fitting practically the formula in parentheses a plus b squared?
Mm-hmm.
Yes. Yeah.
And should we get our answer in algebraic form?
Yeah.
So this why there is no need to convert that in any other form because this is just the second power and we have easy formula which we can apply here. I'm talking about formula a plus b in parentheses squared. This why I am not going to convert this into any other form. If I had here, let's say 2 plus 3i in parentheses to the 10th power, probably I would convert this into trigonometric form or polar form to perform that operation. But here there is no need. So which means, what about the expanded form of that formula? It should be a squared plus 2ab plus b squared. The square of the sum of two numbers equal to the trinomial, where we start with the highest power, which is second, we end with the highest power for the second number. In the middle, we have double product of first number by the second. So let's do that. So it will be 2 squared, which is 4, plus 2 times 2. Let me show more steps. 2 times 2 times 3i plus 3i in parentheses squared. So I first apply that formula, which has a squared plus 2 times ab plus b squared. And now I will continue my simplification. So it will be 4. 2 times 2 is 4, times 3 is 12i. 3i squared, it is actually 9i squared. And we know that I squared is equal to -1, -1. So it is 4 minus 9, and I'm surrounding this in parentheses, plus 12i. So their final answer here is 4 minus 9 is -5 plus 12i, and that's it. I don't need to convert this in any other form because I got my answer in its algebraic form of that complex number. Questions?
No.
No.
And now, from the same spot, I would probably solve not only problem number 14. I prefer to show you more problems from this spot so you will see how I can work with these problems. Again, you are equipped by 3 forms: algebraic form, trigonometric form, polar form. You have three forms. And let's see what can be done, let's say, with problem number 11. What do we have here? We also have the second power, but the number inside of parentheses is not anymore in its algebraic form. It is I times pi over 3 with the square outside. You can have this I in front of pi over 3. If you like, you can have it pi over 3 times I. It will be also absolutely normal. Okay. Does it look like a power to the power?
Yeah.
Yes.
Yes.
Because can you look at the piece which you have inside of parentheses? Does it look like a power to you? Yes?
Yes.
It
Yes.
has base E.
Yeah.
Exponent is I times pi over 3. Outside we have second power. What do we do when we raise power to the power? Do we keep the same base?
Yes.
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 Write down without parentheses, write this E base. What do we do with exponents?
We multiply them.
Definitely. So if you multiply them, what will you get? You will get I times 2 pi over 3. Is it correct?
Yes.
Yeah.
So write it down. But what I have right now represents a complex number, but in what kind of form? Is it a polar form now? Guys, I asked you a question.
Yes.
Yes.
Yes, because you can say exponential form or polar form. There are synonyms for complex numbers because it looks like exponential form. It looks like a power. This is why it is an exponential form here. And at the same time, your book calls that form as polar form. It is perfectly okay with me. But I cannot move directly from that form to algebraic form. I need to have a middle person which can help us to achieve our goal. And this middle person would be our trigonometric form. So practically, right now, we can use so-called Euler's formula. And Euler's formula is right here on the top of my paper. This is in the box, this is the Euler's formula, how we can convert polar form into trigonometric form. So let's do that. So this E to the I times 2 pi over 3 will be equal to cosine of 2 pi over 3 plus I sine of 2 pi over 3. I used Euler's formula to convert this into trigonometric form. And now, using trigonometry, I would simplify each of these cosines and sines of this angle to get algebraic form. 2 pi on the top of each of these fractions representing angles. Can I convert this into 3 pi minus 1 pi?
Yes.
We did it again so many times. 3 pi minus pi over 3 plus I sine of same thing, 3 pi minus pi over 3. And I will go to the next step and I will write that it is cosine parenthesis 3 pi over 3 is pi. So it will be now pi minus pi over 3 plus I, and the sine also after that symbol of sine, I also write absolutely the same angle. So this is what I got. And now I'm going to apply that European rule, which I actually taught you already a while ago, to simplify each piece. Pi minus pi over 3, is it the angle from the second quadrant?
Yeah.
Guys, I expect more voices. I really apologize.
Yes.
Okay.
Yeah.
In the second quadrant, cosine is positive or negative?
Negative.
Negative.
Put minus, absolutely correct. And should I keep the same cosine or switch to other function?
You can keep it.
Why? Because pi was a horizontal quadrantal angle. Absolutely agree
Yes.
with you. Thank you very much. And the reference angle was pi over 3. So it will be minus cosine of pi over 3. In the same manner, I will work with sine. So please write I as I did and think about what should you multiply by this I. You have sine of pi minus pi over 3. This is same angle from the same second quadrant. In the second quadrant, sine is positive or negative?
Positive.
Positive. Should I keep same function sine or switch to another one?
You can keep it.
Keep it. So it will be I sine of pi over 3. So you converted this into that form, minus cosine of pi over 3 plus I sine of pi over 3. But pi over 3 is the reference angle. You can find the value of sine and cosine and all other 4 trigonometric functions for pi over 3 at any textbook in special boxes where they provide values of commonly used reference angles. So we can proceed right now to algebraic form. So I'm putting down that minus. What about the value of cosine of pi over 3? What it is equal to?
1/2.
Accepted. Thank you very much. Now, look at the next piece. Sine of pi over 3. What is the value of that?
Square root 3 over 2.
Also accepted. Very nice. Thank you very much. It was very helpful. I deeply appreciate your help. So, and I am already boxing the answer. Voila. This is my answer, which now is in its algebraic form as book requested that. Questions about that last problem, number 11. Did you understand how I reached that answer?
Yeah.
Can I move to
Yes.
other problem?
Yes, please.
Yeah.
I really recommend you to copy problem number 14. And while you try to start working with this problem in the same practically manner as I did in problem number 11, I will check your attendance and I will join your company solving together that problem. Is it okay with you?
Yes.
Thank you very much. So what do we have here? We have fourth root of what? 10 multiplied by e. You have e to the what power? I times pi over 2. I will help you right now with the first step to show connection between number 14 and 11. And after that, I will read your names. So this is that problem. I copied that. The only difference, instead of pi over 2 in the slashed form, I wrote it like a regular fraction. I really recommend you to convert this radical form into exponential form. We know that we can move back and forth, converting radical form into exponential, exponential into radical as many times as we need. Let me write on the side a reminder how we do that. So let's say we have a root which has index m, and we have under the root in radicand, we have that nth root of a to the nth power. So this is the radical form, but if I like to convert this into exponential form, it will be a to the n over m. Index goes into here. Denominator you can see, oops, that you cannot see. A to the n divided by m. So this y, what is the index in our problem of that root? Is it 4?
Yes.
So convert this into 10 times e to the I pi over 2, surround by parentheses, and right outside 1/4, replacing that radical form into another form, by another form, excuse me. So you have a power. And now this is the cousin of problem number 11. Can you please start working with that? And I will be with you shortly. Let me grab your roster. So we have again missing people, but it is their business, definitely, what to do with their lives. Okay, so today is May the 1st already, new month. Congratulations with the beginning of last month for this semester. So, Andrew, I'm checking the names which I have right here. Okay, Tima, Lorraine,
Here.
Lynn,
Here.
Juanita,
Here.
Yuran,
Here.
Gabriel,
Here.
Divina,
Here.
okay, Chantal,
Here.
Gongsi,
Here.
Kyle,
Here.
Matthew,
Here.
Julian,
Here.
Nathan,
Here.
Alejandro.
Here.
Thank you guys. So what I'm going to do, I'm going to raise right now expression in parentheses, which I can call as a product of 10 and that power with base e. I need to raise this to the 1/4 power. And how do we raise products to any power? We need to raise each component of that product, which we call factors. So one factor here is 10. Another factor here is that power with base e. So it will be 10 to the 1/4 multiplied by e to the I. I'm showing all details right now. So you have now that new product. Each of these components carries its own 4th power. What I'm going to do right now, I'm going to proceed here. So it will be here, what? 10 to the 1/4. You know what? Up to you what to do, because we probably will be using our calculators to approximate. Definitely, if you like, you convert 10 to the 1/4 into 4th root of 10, back going to radical form. But I probably would leave it alone because we will be approximating, and it is much easier for us using our calculators to have that in exponential form. So I would not do anything with that. So now I'm writing 10 to the 1/4. Now let's talk about this power. Is it again power to the power?
Yes.
Yes.
And can you help me, please? What should I write now? We already did that in the previous problem. Should we multiply exponents?
Yeah.
Yes.
If you multiply, what do you get? Is it pi over 8?
Yes.
You can see, I wrote it down. And now, this is the only thing what I can do with that exponential forms, right? I need to get my answer in algebraic form. What do you think? Is it now the most proper time to go to trigonometric form?
Yes, it's fine.
Yes, definitely. I am going to use Euler's formula right now, but Euler's formula should be applied only to that part, which has that power with base e. So I am going just to copy 10 to the 1/4. I will open parentheses, and my theta angle is pi over 8. So I'm writing down cosine of pi over 8 plus I sine pi over 8. And I do not have exponential form anymore for that power with base e. I used Euler's formula. Pi over 8 is a very, very simple angle from the first quadrant because it is half of pi over 4. So it is practically 22.5 degrees. So definitely it is in the first quadrant. Both cosines are positive, well, cosine and sine and all other functions of that angle are positive because angle is from the first quadrant. So I don't need to do anything to change that pi over 8 to any other form. This why it is time right now to use our calculator, but to simplify the process, instead of separately approximating cosine of pi over 8 and sine pi over 8, and after that approximate separately 10 to the 1/4 and multiply these numbers, because when you approximate many more times than you could, your answer will be quite far from perfect. This why what I'm going to do, I will distribute right now that 10 to the 4 multiplying by each term in parentheses. So it will be 10 to the 1/4 times cosine of pi over 8 plus 10 to the 1/4 multiplied by sine of pi over 8 in parentheses, and behind this parentheses I would place I, or if you like, in front of these parentheses. You can see I distributed 10 to the 1/4 using distributive property, multiplying by each term inside of parentheses. And now grab your calculators. Because our angle comes in radians, turn your calculator on, and first thing what you should do, check the mode. Press the mode button. So on the third line, I have highlighting at reading. So I have peace in my mind. My calculator is in the readings mode. I press second button, the same button mode, and I'm back to my home screen. And I'm going to enter entire piece at once. What do I mean entire piece? Not separately, cosine of power, not separately, 10 to the 1 4, all together. So I'm starting 10 to the parenthesis 1 divided by 4, close parenthesis. So this is how that piece looks. Times cosine, and again, I have power 8, second button, that corner button, which releases pi, divided by 8. Ten to the 1/4 times cosine of pi over 8. And now push enter to find the value. And let's say we're approximating to the nearest, let's say, thousandth. So which means 3 digits after decimal point. Right, approximately equals to, and I have 1.642 and 9 after that. So I will be approximating this to 3. So this is the first part, approximately 1.643. Plus, I'm doing same thing with that second piece, which we had in parentheses, 10 to the parenthesis 1 divided by 4, close parenthesis, times sine. We have button which says sine, second power, button power, pi is released, divided by 8, close parenthesis, and do the same thing. Entering. Let me actually do that just a single piece on the screen so you can see that better. Just 1 second. To the 1 divided by 4 times sine, parenthesis, second. What is going on? Just 1 second. My calculator is on strike. I probably need to change batteries. Times sine of pi divided by 8. And this, what I got, can you check what you have on your calculators? You can see I have after the decimal point 6805, so plus 0.681, don't forget I. So this is now your algebraic form. Definitely it is an approximation. And I am done with that problem. Did you understand how I worked with that problem?
Yes.
Do you find similarities between number 11 and number 14?
Yes.
Yeah.
Excellent. So I would like to say right now a few words about de Moivre's formula. It comes on page 391 in your textbook. And this is an awesome formula. It is, I cannot even call it like a good formula because it is a genius. De Moivre was just a genius person creating that formula. And let me write down that formula and I will explain everything what I should explain about this formula. It is again on page 391 in your textbook. This is de Moivre's formula. De Moivre, he was a genius mathematician from France. So what do we have here? cosine theta plus I sine theta raised to power p equals cosine of pi theta plus I sine of pi theta. This is the Moivre's formula. I box that. This is a very powerful result. First thing what it helps us to raise any number given in trigonometric form to any power. This why before solving any problem, I will show how it will work if you need to raise, let's say, any complex number given in the trigonometric form into any power, not just second power or cube. Let's say raising this to 22nd power. So if your number z is given in its trigonometric form, and if it is given in its trigonometric form, like z equals to r times cosine theta plus I sine theta, then z to the n power, z to the n power will be equal to, according to that de Moivre's formula, r to the n power cosine of n times theta, plus I sine of n theta. And we came to another formula. We definitely use de Moivre's formula to write it down. How to raise any number, I'm talking about complex number given in its trigonometric form, into another trigonometric form using de Moivre's formula. And this why right now I can solve, showing application of this information, I can solve quite many problems from page 393 from your textbook. Did you have an opportunity to write this down on your papers?
Yes.
Yeah.
And specifically what you have here on the bottom, because unfortunately your book did not have that formula for z to the n power, but it is easily we can get from de Moivre's formula. So let's say I will be working right now with problem number 28, which is on page 393. Problem number 28, page 393. What should I do here? Use Euler's formula to here to, okay, and the identity, okay. Okay, I understand. So basically what I need to do here, I need to prove that formula. What kind of formula? That sine of 2 theta equals 2 sine theta times cosine theta. But you know what? Right now, I practically, even though I declared problem number 28, I will do something to prove two formulas instead of one. Basically, I will prove formulas in number 28 and problem number 29 at once. So I will be proving this formula and another formula. Both are coming from trigonometry. Yes, we can use just pure trigonometric methods to prove these formulas, no problem. But this is another way to prove these formulas and much easier than trigonometric proofs, actually. What should I do? I would be doing what? I will have my original number z in trigonometric form, and let's say it is r times cosine theta plus I sine theta, given part. Z equals R times cosine theta plus I sine theta. I'm not going to do that through Euler's formula because I can do that easier than book requests. So look what I'm going to do. I will raise that Z to the second power. Z squared equals R parenthesis cosine theta plus I sine theta squared. Which is R squared cosine theta plus I sine theta squared. Agree?
Yeah.
Yeah.
Now I will just copy R squared, but I will apply de Moivre's formula to that parenthesis with square. What should I do applying that de Moivre's formula? I just need to multiply theta after cosine symbol and sine symbol by 2. So it will be cosine of 2 theta plus I sine of 2 theta. Agree?
Yes.
Yeah.
Now, I'm going to work just with the last line here. So I'm going to consider these two underlined expressions, and I'm going to work with these underlined expressions separately right now. So I have R squared. Now, on the left, I'm going to expand this using just algebraic formula A plus B squared. A is cosine theta, B here is I times sine theta. So it will be cosine squared theta plus 2 times I cosine theta times sine theta plus I sine theta squared. Again, what did I do? I used formula of A plus B parenthesis squared, which is A squared plus 2 times AB plus B squared. So far, so good?
Yes.
Yeah.
Which actually, according to what I came to on the previous line, will be equal to R squared cosine 2 theta plus I sine of 2 theta. Can we divide both sides by R squared, guys?
Yes.
Yeah.
Cancel them. They are gone. What is left? You have cosine squared theta plus 2I cosine theta sine theta plus I squared times sine squared theta. Is it correct?
Mm-hmm.
Yeah.
Which is equal just to cosine of 2 theta plus I sine of 2 theta. Now, look at this last term on the left. Is it negative sine squared theta?
Yes.
So just convert I squared into -1 and you will get this result. Write down the real part of that plus imaginary part, and I will show you how I wrote it down. And copy the right side. And now we are ready to get that formulas which we had to prove. Are you with me?
Yes.
Yeah.
Did you copy that last line?
Yes.
Just one person?
Yes.
Yes. What do we have on the last line? We have one complex number on the left, another complex number on the right. The equal sign in between, it means these two complex numbers are equal to each other. We already talked about that yesterday. We cannot say which number is greater or less than the other one, but we can say if the numbers are equal or not. And they will be equal only if their real parts are equal to each other and their imaginary parts are equal to each other. These two numbers, they have real parts, and I'm going to underline real parts, and I will be using wave to show imaginary parts. Do you agree?
Yes.
Yeah.
So real part is equal on the left, cosine squared theta minus sine squared theta. It will be equal to the real part on the right side, which is cosine of 2 theta. And this is one of formulas for cosine of double angle, which we just proved. And the two, I prefer to, instead of 2 cosine theta, write 2 sine times theta cosine theta, because A times B equal to B times A. I just like to write this in more traditional way. Will be equal to the imaginary coefficient on the right side. And voila, we proved that two formulas. This is from number 28, and this one from number 29. So with one hand, I caught two birds. So formula de Moivre is a genius formula which can help us to quite easily prove formulas for cosine of, let's say, 10 theta, sine of 10 theta, because practically in your books, you maximum have trigonometric books, you have cosine of 2 theta and sine of 2 theta. But for example, when I was a student taking trigonometry class, it was during my high school years. So I learned formulas, and for 3 theta also, cosine of 3 theta, sine of 3 theta, but we never basically used formulas for cosine of 4 theta or sine of 4 theta. But using formula of de Moivre, we easily can prove that formulas as well. This is why I call this formula de Moivre like a genius formula. Do you understand what I just talked about?
Yes.
Yeah.
For example, if you need to prove formulas in number 30 and 31, you can use absolutely the same approach easily. Only raise, this time here we raise to the second power. Now you need to raise your z to the negative first power. Is it clear?
Yeah.
I wanted to show you another very beautiful example. Unfortunately, I don't have time to continue, but I definitely will show that on Monday. But can you please tell me about the due date for that homework from 9.6?
I think it's due on the 5th.
On the 5th. Okay, so we will have time. So I just was concerned about that.
Yeah, it's due on Tuesday.
I hope that you understood some of, I definitely like to show a little bit more. This is why I'm saying I like to show you more examples. So, and I will do that on Monday, because it is just one section. They did not cover many important things because it was impossible to do it just in one section. This is why I decided to show you a little bit more material than book actually did. And I hope that you will appreciate that when you go to upper level of classes. If you are a little bit unhappy right now because I showed you more material, but I am sure you will appreciate that later. So anyway, So please, each time I really recommend you to take really detailed notes, because usually during my lectures, I show you some additional methods and information than book just had. It is impossible to show everything in one textbook because it will be so huge that people would not be able to carry that textbook around. So this is why we cannot blame publishers, but again, many professors are equipped by much more information and material than book usually has. This is why I all the time recommend my students to have really detailed notes. With your permission, can I finish my today's lecture?
Yes.
Yeah.
Thank you for being today during my lecture. I wish everyone beautiful, nice weekend. And please constantly watch what you have on your Wiley Plus. And as I already mentioned, on coming Monday, you will have your, as we call, in-class quiz, but it will be offered to you at the end of Monday's lecture. So everyone have a nice day, and again, stay well and safe. And can I say goodbye right now?
Mm-hmm.
Bye.
Bye, guys. And again, stay healthy and safe. And please don't forget about math material. Okay,
Thank you.
goodbye.
Bye-bye.
You're welcome.